Okay, so now we're going to be discussing about the last operation, which is a curl. And we're going to use the same vector field that we discussed with divergence. Here, because the notation is rather long, we're going to be just shortcutting the notation, and we don't have to write det of this of a matrix. So first, we have our curl. What I'm going to do is just use a vertical bar to denote each respective direction. Or I'm going to use a vertical bar, and this is a common notation just to talk about determinant. Now, first we have the partial derivative of x, the partial derivative of y, and the partial derivative of z. Then we have x squared e to the xy, and then sine of z. Now, it would be rather long if we kept having to break it down into subdeterminants. So this is the devised shortcut. And this shortcut isn't because I made it up, it's because it's just a pattern that is seen. So we have, and this only works for 3x3 determinants. What we're going to do is create a kind of a trapezoid as such. X squared e to the xy. Now, whatever we multiply to the left, whatever we multiply to the right, we will denote it by a plus. Whatever we multiply to the left, we multiply by a negative. And we just sum them all up. So we have, in the x direction, the partial derivative of y on z, which is 0. Then the partial derivative of z onto y, which is also 0. So we have the first operation here. Then we have the second operation, the partial derivative of z acting on x, minus the partial derivative of x acting on z. So we have ay, which is going to be 0 minus 0. And then lastly, we have the partial derivative of x acting on xy, and then the partial derivative of y acting on x. So we have az. This becomes y e to the x minus 0. So the curl of this is 0ax plus 0ay plus y e to the x az. Now, if you notice, if we had to do this the formal way, this would take us maybe a good 5 minutes. But by drawing a trapezoid of this following shape, and this shape is mainly a shortcut from another method of calculating the determinant, we're able to quickly one-shot the calculation. And as such, we get the following divergence. Now, from here, I want to propose the following idea. What if, in general, this curl was 0? Now, we can't say it's just 0 because that would imply that this is a scalar, which it's not. So I denote it by a 0 vector. Then this notation is not unique. This is how we notate it. Now, what this is telling us is that this thing does not rotate. And as such, this thing actually diverges. So this thing, while it rotates, may be may be diverging. And let's suppose that in the event that it doesn't rotate and it doesn't diverge, we get this famous relation the that all the vector lines are completely parallel to each other. They don't diverge from a source, or they go into a sink, but they instead, and they certainly don't rotate either. This is in the case of a perfectly symmetrical case where, for let's say for an electric field, this electric field is very easy to calculate. Pretty much this vector field is kind of uniform, so as to speak. But that's just kind of just to give a little preview about the meaning of when a curl is equal to 0. It could mean that its divergence it's not 0, but in the event that it is both 0, then we have that the vector field is parallel. So that's just, we wrapped up the 3 operations from gradient to divergence to curl. And next we're going to then be discussing about the applications of gradient, divergence, and curl. All right, thank you.